This is an instructional video about equivalent expressions, and our essential question is what makes an expression equivalent to another. So the first piece is equivalent expressions. Those are always equal to each other. So for example, I have a plus 2 plus 3 is the same as a plus 5 because they are always the same for any value of a. So if I made a 1, I get 1 plus 2 plus 3, which is 6. And if I make a 1 here, 1 plus 5 is 6. So they're always the same. However, if you look at this, a plus 5 and 3 plus 4 are not equivalent because they are only the same when a equals 2. Because 3 plus 4 is 7, and if a is 2, 2 plus 5 is 7, so that's when they're the same. Otherwise, they're not equivalent. And so we're just going to say those are not equivalent expressions because they're not always going to be equal to each other. Before I continue with this piece down here, there's one piece of notation that I want to make sure that we're confident with, is that we can drop the multiplication symbol as long as it's not between two numbers. So for example, if you saw this, if you saw AB, it means A times B. If you saw this, it means the same thing as 4 times P plus 6. Now the reason we can't do it between two numbers, we'll take a look. Here's 23. Is that the same thing as 2 times 3? No. So we can only do it between a number and a variable, or two variables, or a number and something grouped in parentheses. So that's just a notation I wanted to make sure that you were comfortable with because we're going to be using it. Now, these two pieces here, I have examples. So we have a situation and a diagram, and we're kind of building a basis of how do we write equivalent expressions. So first up, we have 3 identical packages weigh 1/5 gram each. So I drew a diagram, 1, 2, 3 packages, each 1/5. Well, if someone's asking me for the weight, I would add them together. So with addition, it's 1/5 plus 1/5 plus 1/5. Because I'm just looking at here, this one plus this one plus this one. If I think about it with multiplication, I have 3 of these, and they're each worth 1/5. So it's 3 times 1/5. Well, without multiplication, if I look, it's just 1, 2, 3/5. Now this is in the context of using fractions to kind of connect it to this is how we do it with numbers. But now what if we have a variable? And a variable is just a letter we use saying this spot's kind of saved for something. We don't know what it is, or we do know what it is, but we just always want to show that this spot is going to be saved. Kind of like when you go to church or a wedding and you put your jacket down to save a spot for someone to come sit next to you. That's what a variable essentially is. So this one here, I have 3 identical packages weigh m grams each. So I got 3 packages, and they're each m grams, because we don't know what it is. Well, if I was to find the total weight, it would just be m plus m plus m, which is the same as 3 times m. But like we talked about here, I can get rid of that multiplication symbol, so it's 3m. So let me show you one more. I got 2 boxes hold b books each, which is b plus b, which is the same as 2 times b, which is the same as 2b. Now how about this one? I have 4 bags hold C peaches each. So I'm going to draw 4, because I see 4. C, 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 which is the same as, if I'm looking for total weight, C plus C plus C, which is 4 times C, which is the same as 4C. Now the reason that we're kind of making sure that we have a good understanding about this is because we're not just going to be using situations like this with algebra. We're also going to be using equations and algebra tiles. So, algebra tiles. There are 2 types of algebra tiles that we'll be using as 6th graders. There's one that looks like a rectangle, which usually stands for your variable. We usually use x. And then there's a square, which stands for 1. So, if I was to make an example, well, I'm going to look here, and I'm giving this to you. So this is not something you're like, well, how do you get that? I'm just giving it to you. Well, I notice I have x, x, and x, and 1 and 1. Now, some students can look at this and instantly see what the equation is. Oh, sorry, the expression, not the equation, the expression. But some students, we kind of need some help and support. So I'm going to use the information I had on the back to help me. So I notice I have 3 x's. So that's with addition. That's with multiplication. But we don't need that multiplication symbol because I know notation-wise, I can just write it as 3x plus, and then I have 1 plus 1, which is 2 times 1, which I don't need to take out. It's not going to be 21. What's 2 times 1? It's 2. So I took my picture and I drew the expression that it's equal to. Now reverse. I want to model 4x plus 3. Some students know exactly right away, what do I draw? But for those of us who are struggling, let's take this and work backwards, which is 4 times x, which is x plus x plus x plus x. So I need 4 of those rectangles. And then I have 3, which is 3 times 1, which is 1 plus 1 plus 1. So there you go. So this is the first step that we started working on in Math 6 to kind of help build a general understanding of how to create equivalent expressions and how do we use models and diagrams to help us generate those equivalent expressions.